Hello everyone, welcome to webinar on flat slabs as per American standard, that is ACI318. I am Niveta Khole, Regional Technical Manager at MIDAS IT. If you have any questions, you can write at the box or you can send us an email at techsupport@midasit.com. Before I begin with the session, let me introduce you to MIDAS Software Solutions. MIDAS as a company started in 1989 and it has distributions in over 120 countries. There are 540 number of employees, 18,000 number of clients and more than 40,000 number of users worldwide. Biggest CAE software developer in civil engineering is MIDAS. MIDAS has got its core softwares in bridges, structures, geotechnical and mechanical. So under the bridges, MIDAS has got MIDAS Civil, which is an integrated solution system for bridges and civil structures. So any type of bridge can be modeled within very short period of time and designed as well. So after that we have MIDAS FEA, which is for advanced nonlinear and detailed analysis. Going to the structures part, we have MIDAS Gen, which is integrated system for buildings and general structures, in which you can analyze and design building structures. Even general structures can be analyzed and designed. Then we have MIDAS D-Shop, which is an auto drafting and rebar detailing module, which can also generate bill of materials. MIDAS Design Plus is a structural component design as well as detailing software solution, and it can also provide with a bill of material. Under the geotechnical, MIDAS offers 3D as well as 2D software solutions. GTS NX is a 3D finite element based software solution, geotechnical software solution, and SoilWorks is 2D finite element based as well as analytical based geotechnical software solution for practical design. And the mechanical part, we have MIDAS NFX and MIDAS FX Plus. So in this session we are going to be performing the entire model by creating the geometry and providing the material properties, section properties, and further we are going to apply the boundary conditions, apply loads onto our structure, and further go ahead perform the analysis. After the analysis we will be checking the analysis results offered by MIDAS. And after the analysis results, we are going to be discussing on the design methods and also the design provided by the software solution, which includes the Flexural design. Software can also perform the check after the user provides the reinforcements. Then slab shear check will be performed. Then slab serviceability check will be there, in which we'll also be performing the cracked section analysis. Under the modeling, we are going to be creating a structure, a simple structure over here, a square shaped flat slab with the columns having material properties as 35, C3500 and slab having C2500. The column section will be 600 by 600 mm and the thickness of the slab will be 180 mm. The load that we are going to be applying onto our structure is the self-weight as well as a live load, that is the pressure load onto the slabs, which is 8 kN per meter square. Let us go to MIDAS Gen software to start with the modeling. Go ahead and click on New Project. If your license information is correct, you'll see a blank screen. So let me explain you quickly about the user interface of MIDAS software. Here we have got the ribbon menu, which is having different tabs, and all these tabs are aligned as per the workflow. So first we create the geometry, assign the properties, and then assign boundary conditions, apply loads, perform the analysis, check the results, and then perform the design. Then we have got all these tools in the shortcut toolbar. The view points will be seen over here very easily. You can change the view, isometric, front view, top view. After that, we have got over here the tree menu, which will be focusing more on the footworks tree menu. So this is a very special feature in which you can, our intuitive feature in MIDAS Gen, in which by one glance you can understand what all things have been incorporated in the model. Right now there is no model as such, so no information. Further, we have got the message window. If there is any error or any warning, then you can see it right over here. Even during the analysis or after the analysis performed, you can see the message right over here. The unit system can be changed at any point of time. I've kept it as kilonewton mm. I can change it to kilonewton meter. So let us start with the geometry. In MIDAS Gen, we can create the geometry by using 4 different methods. Firstly, we have got the importing option, in which you can have 2D, 3D, CAD, DXF file imported. SAP files, STAT files, CTABS files can be imported in MIDAS Gen. The next one is about creating wizards. So these are all the wizards available for creating the geometry. Next is about the dimension grid lines, define line grids basically. Then we have got the different types of tools available to directly create the structure onto the workspace. In this session, we are going to be using the third type, that is the grid line system. So firstly, we'll define the line grids in the X and Y direction. For that, I'll click on Add. I can have more than one grid line system, so I'll firstly create one, in which the first grid line spacings, I'll click over here to add. I'm making a simple structure like shown before, so we're having 2 numbers of spans at 0.6 meters each, then 1.3 meters apart. We have the same spans 3 times, so I'll just select this, copy and paste it twice. And lastly, we have again 2 at 0.6 meters span. So with a comma, you can provide the next spacing, and then I'll click on, before I click on OK, I'll just copy this entire information because it is the same in the Y direction as well. So I've copied it and I click on OK. My X grid lines are done. For Y grid lines, I paste it. I paste the same information and I click on OK. After that, I click on OK again, and to apply it onto my workspace, I click on OK. So here we have the entire grid line onto our screen. I can go in the top view and have a better result. Now let us go to the Node Element tab to create the nodes and elements onto our line grids that we have defined. So firstly, I'll create some nodes for the columns. So these nodes I can just simply click and create on the intersections of the grid lines. However, I want them to be copied because they are having equal distances. So there are 3 times equal distances in the X direction that can be done by using this copy command inside this particular tool. So I'll make it 3 times, and the distance I'll have it from here to here. So over here I have to specify the coordinates. So coordinates you can manually specify, or you can just simply click on this box. As the box turns green, you can click on the intersection of the grid lines. So I'm clicking right over here, here, here and here. So as you can see over here, after I clicked on this intersection, 3 nodes were automatically created. So my nodes have been created. After that, I can also create the line elements. So here I'm going to be creating the line elements directly onto the line grid. So I'll click on nodal connectivity box right over here, which can also snap on to the grid lines. The snapping tools are available right over here. So I will snap on to this intersection, to this, and similarly from here to here. What I'm doing right now is basically creating some dummy elements so as to create equal sized, or I can create the subdomains as required, as required by me. So now that my dummy beams are created in the X and Y direction, I can just simply copy them further on the other locations. So I'll copy these X ones in the Y direction. For that, I will use the translate elements command. This will be done again 3 times. I can do it, and the equal distance can be taken from the software. You do not have to measure it as such or calculate from your calculators again. So I'll click over here, click on one intersection to check on the grid line snapping, and to this. So 2.5 meters it has detected. All I have to do is click on apply. So what I did was simply select the elements, provided the distance, and clicked on apply. So my beams, dummy beams are created. Next thing I want to do is create my columns. Now I can similarly create grid lines, or maybe create more number of nodes and use create elements to create from one node to the other node by clicking on one node to the other node. However, MIDAS Gen has got this very interesting tool, that is Extrude Elements, a very useful feature which can convert our nodes into line elements, line into planar, and planar into solid elements. So I'm going to use this nodes to line elements, that these nodes which I created for my columns will be converted into a line element. Okay, so I'm going to be selecting all these nodes. Okay, after these nodes are selected, I will provide the distance, let's say minus 0.5, and I click on apply. So if you see in the front view, your columns have got generated, or in the isometric view also you can see the entire structure. After the columns are created, now let us go ahead to create the slabs. Flat slab. To create the flat slab, you can at any point of time create an entire plate element and then further go ahead and mesh it. That comes under the meshing, auto meshing tool, or the map meshing tool. However, MIDAS Gen has got other methods as well for creating the mesh for your plates. Instead of firstly creating the entire plate and then performing the mesh, MIDAS offers line elements or nodes type of method. All you have to do is select the lines, select the type of mesh you require. I'm using quadrilateral plus triangular. We have got 3 methods available, 3 types available for meshing. Then provide the mesh size, let's say 0.24 meters. Okay, I'll go to the front view and select all the beams or the line elements lying in this particular plane. So as you can see over here, all the beams have been selected. So I've selected them and then click on apply. So as you can see over here, very quickly the mesh has been generated, and if you have noticed that over here at the center, the nodes for the column top has also been included in the mesh. All the nodes have been included for the mesh. It has automatically changed the mesh type, and then it has included that node into the entire plate. So in this case, you do not have to worry about the nodal connectivity. Next thing is about the local axis of the plates. These local axes are not oriented according to the global axis. If we can see that in the display tool, element, local axis. Okay, so I'll have a closer display. So as you can see over here, that the orientation of the local axis is not the same for every element. It is different. So to align the local axis of each and every element so as to provide the reinforcement direction to the software, we'll go to the change parameters. Go to the element local axis, select the planar, coordinate direction, and the local x of each and every planar element will be aligned to the global x-axis. Okay, so I select all the plates and click on apply. So in this way, the local axis of the plate elements have got aligned with the global x-axis. So we have done with the modeling of our geometry. I'll undisplay the local axis again. Okay, so after we create the geometry, we'll go ahead and define the properties. So in the properties, firstly we'll have the material properties. Okay, so let us firstly add the material. This is an RC flat slab, so the type of design that we're going to perform is concrete design. We do have steel and SRC, also user defined material can be created. So concrete, standard, there are huge number of standards available in MIDAS Gen. We are going to be using American Standard, and we are going to select the grade from the database available as per the codes. So firstly, grade C3500, and this name I'll change it to column because I want to apply it to the columns. The material property parameters can be seen right over here. Modulus of elasticity, Poisson's ratio, thermal coefficient, weight density, all these are available right over here. And if you want to make changes in these properties, you can simply change this to none, and these are editable then. However, I'm going to be using from the codes. So grade C3500. Then I'll click on apply so that the dialog box won't close, and I can go ahead and create or define another material property. So this will be for the slab, and the grade is C2500. I'll click on OK to close the dialog box. Next, I will define sections. So here again the same features are there. I'll be adding. Firstly, I'll add a dummy section property. So I do not want to consider its stiffness at all. It was just for creating the subdomains. So I'll go to the user, and here I will provide a very minimum value. I'll click on apply. So my dummy section property is created. Next, I'll create the column section property. So this is going to have the shape of solid rectangle, and here according to the reference image I can provide it as 0.6 by 0.6 meters and click on OK. Further, I'll go ahead to the thickness and click on add for the slab thickness property. Now here we have got in plane and out of plane thickness. So here I'm going to be using 0.18 meters. If you want to have the slab as a membrane type, then all you have to do is membrane in which you have to consider only the in-plane forces. So in that case you can go to the in-plane and out of plane option right over here and just provide the thickness in the in-plane. I'll click on OK and close. Okay, so here I can have different color options. It's all in red, so I can just change this by going to the display option tool. I go to the draw and say random color and say apply and click on OK. So here I have got the entire geometry created along with the properties defined, and now I can go ahead and assign the properties correctly, because the slabs have already been assigned with the first thickness property that we have defined. So I'll just close this, and here we have got the material properties. The first material property that we have defined is assigned to the entire structure. Now I want to assign the slab material property, so I will go to the front view, or instead of that I can just double click on the plates. The plates are the slabs, so the plates are selected, and then I can simply drag and drop on my workspace, and the slab property will be assigned only to the slabs, not to the columns. Okay, so column and slab property has been assigned. Next is the section property. Now dummy elements have been assigned automatically with the dummy section property because it is the first property. So all I have to do is select all the columns. So these are the columns that I'm selecting. Okay, so all the columns are selected and I drag and drop the column section property. So I'll just show in the front view. Drag and drop. Select, drag and drop. See? Within very less time we have created all the we have assigned all the column property. Okay, so the first thickness property has been assigned to the slabs automatically. Now for a better view I can just turn off the nodes, and also I can see from the top the columns, but for that I need to create blending color property for this display. So for that I'll go to the display option, color, thickness, blending. Yes, okay, so now it has blend with the column, and now I can see the column thickness or the column section property from the top view. Okay, so after the properties, let's go ahead to the boundary conditions, and we'll apply the supports to our nodes at the bottom of the columns. So I'll select all the nodes at the bottom of the columns from the front view, and now here the command is open. So when I check on these boxes, it means that the translations in the X, Y and Z direction are restrained, and if I check on these boxes, then rotations in X, Y and Z directions are restrained. So I have selected the nodes, checked on the boxes for restraining or constraints that I have to provide, and I click on apply. So the boundary conditions have been applied. There are other available tools in MIDAS Gen. When it comes to mat foundation, you can apply the surface spring supports, wherein you just have to provide the modulus or subgrade reaction to the software, and the software will calculate the surface spring stiffness automatically. The best part in the software is that it not only converts the surface springs to nodal springs, but also creates distributed spring supports, which is much practical. Okay, so after applying the boundary conditions, let us go ahead to the loads. Under the loads, we're going to be in this session applying the gravity loads, and that to static gravity loads. So we are going to be creating firstly the static load cases. So I'll provide dead load, and the type will be dead load. I'll click on add. Now these types are important because the load combinations will be automatically generated by depending on the types that we have selected for the load cases that we have created. So I'll click on add, dead load and live load, and I'll close. The other types of loads that can be applied in MIDAS Gen are dynamic loads, which includes the response spectrum, and the time history functions are available, in which dampers and isolators can also be incorporated. Then we can perform temperature analysis, and also pre-stressing can be performed in MIDAS Gen post-tensioning. Beams and slabs can be done. Then construction stage analysis can be performed for column shortening analysis. We'll be having a session on column shortening also on 18th, so hope to see you there too. Then we have the moving loads. We have different moving load codes available with us for any loads, crane loading, for example, in case of industrial structures, or if you have ramps that you want to analyze, then on that vehicular loads can be applied. So after that we have got heat of hydration analysis for rough foundations more than 1 meter thickness or any mass concreting works, for understanding the differential stresses due to the temperature effects. And to cater to the cracking due to the heat of hydration, pipe cooling system can also be incorporated. So these are the available loads in MIDAS Gen, and we are going to be providing the static loads in our session today. So we have applied the static load cases, and next thing we're going to do is apply the self weight. So we'll click on sulfate, and here we can provide the factor, the scale factor for the sulfate, that will be minus for the downward direction. Z is our vertical axis, so downward vertical direction, and that too 1 times only. So I'll click on add. Under the dead load case, our sulfate has been added. After that, we will apply the pressure load onto our slab. So we have pressure loads right over here. These are under the live loads. Okay, so we can apply live load case onto the structure, onto our slab, or we have another way of providing the pressure loads, that is the load type. So under the load type, you can simply create a typical load type, let's say, in which I include all my load cases. So dead load and live load is there. Let's say this is -5 and this is -8, and then I click on add, close. So I can use this particular load type onto my entire slab. So no need to provide any loads individually for load cases, different load cases. Okay, so I click on all, select all, and apply. Okay, now over here automatically dead load, live load, both load cases have been applied at once onto my entire slab. The initial view right over here, and I'll go to the isometric view. I can turn off these nodes and click on OK. Okay, and I'll go ahead now and perform the analysis. Okay, so within 1.15 seconds the analysis has been completed. A very small structure, of course, but fast. Yeah. So let's go ahead to the results. Under the results, the first thing we'll do is create load combinations. So firstly, we'll have general type of load combination, which will be useful for checking the analysis results. So I'll click on auto generate over here. Why for analysis results? It's because the envelope will be created under the general tab, the strength and the serviceability envelopes. So I'll have this checked on, and then further I'll select the code. So I want to select a concrete code. The huge database again available for us to select from, and because we're going to be performing using ACI standard, we'll click on ACI318-14. Okay, after that I'll just click over here to see the lower OK button from here. So I'll click on OK. So in this way I can see all the load combinations created by the software and the strength and serviceability envelopes created, automatically generated. Further, to perform the design of my flat slab, I need to provide the load combinations under the concrete design tab. So from here itself, the software will take into consideration the load combinations and perform the design accordingly. So this also can be automatically generated. Select the code and click on OK. And you can see that strength and serviceability load combinations have been generated. These load combinations can be also edited. So you can simply change the factors from here. You can see the factors that have been applied by the software from here, and you can make changes as well. And go ahead, close this dialog box and check the results. So the results after performing the analysis, I would be firstly showing with the reactions that we can get for the supports that we had applied. So I'll select the load combination for which I want to see the result. I'm selecting strength, RC envelope strength, and I'll click on values and click on apply. So on the screen, on the workspace itself, I can see the reactions. Wherever this red mark is there, maximum reaction has been obtained. I can also get reactions in the form of tables by clicking right over here in the small box. Select the load combination for which I want to see, And these table can be also copied. I can right click and say copy and paste it in Excel. Or I can directly right click and say export to Excel. I can even sort this entire dialog box. I can sort this entire table by clicking on sorting dialog. I want to see maximum vertical reaction at the top, and I'll click on sort. So here at node number 66, maximum vertical reaction of 164.67 kilonewton has been obtained. Okay. After this, I would like to show about the displacement contour under deformed shape, under deformations. So displacement contour, this will be checked for the serviceability envelope, maximum serviceability envelope. I'll check the deformed shape. I do not want to see all the values on the entire plates but the legend, and I'll click on apply. So this is the deformed shape with the maximum deformation of 0.30 mm. If you want to see this result in millimeters, you can change the unit at any point of time. So 0.303 is the deflection, maximum deflection, and you can see that using these contoured diagram. Now you can as well as create animation of the deformation that is taking place. So for that, I'll click over here and click on apply under the animate option, and then I'll click on record. So what the software over here is going to do is record your animation of the deflection that is going to take place, and this recording is going to be saved as in the AVI file format, which you can use it further for your presentations. I'll stop this animation from here, and then we'll move on to the forces. Under the forces, let us see the plate forces and moments. Let us go back to the Excel. The analysis results for flat slabs, most important are the moments for applying the reinforcements. So in that, MXX, MYY and MXY are the moments required. MXX is the bending moment per unit width in the direction of the element's local x-axis, which is nothing but the out of plane moment about local y-axis of the plate. Then MYY is also the out of plane moment about local x-axis, and the MXY is the torsional moment about per unit width about the local xy plane of the plate. So as you can see in the diagram, the moments are shown, and apart from that, wood armor moments are the design moments, required design moments that can be viewed under the plate forces and moments. Wood armor moments are nothing but the combination of the flexural moments and the torsional moment. So we will discuss more about how the calculation of wood armor moments are done under the design part. Let us see this result in MIDAS Gen software solution. We are going to select the CB max strength envelope. Then we'll check the average nodal results of the plates. We have selected MXX component, and further I'll uncheck over here the deform and click on apply. So this is the MXX result that you can see onto the screen. You can get the result in the form of plate cutting diagram. So for that you can check on right over here, and I will define a plate. For that I will unhide the thickness, and I can define a cutting diagram, so cutting line. So firstly I'll define the cutting line by providing the point 1 and point 2 to the software. As the box turns green, that means we can go on work on the workspace, that is on the model. So let us create a cutting line along this particular line, and I'll click on add. Okay, and then I click on apply. So as you can see over here, this is the diagram that we can see. I can as well see the negative moments by clicking on reverse at the top. I can as well get this particular diagram in the form of graph. So I'll click on apply. So here I can get the moments per unit width, which can be further used by multiplying with the unit width of the element and then using for the design of reinforcements. For understanding the values at every location of the cutting line diagram that has been defined, I can simply right click on this graph and say save graph as text. So here we go, we have got all the moments per unit width in the X direction, which can be further copy pasted into the Excel sheets. Okay, so similarly we can get we can have another cutting line diagram for finding out the moments at the supports in the X or the Y direction. So let me create a Y direction on the supports. So these are the supports, and I've created the cutting line. I'll uncheck the first line and I'll change this component to MYY and click on apply. So I've got the graph, and also I've got over here the diagram. So I'll unreverse it and I'll click on apply again. And the cutting line diagram in the form of graph is also shown. In this way you can see the plate forces and moments, the forces, the shear forces in the X and Y direction, as well as the wood armor moments. The next thing we're going to do is perform the design for our flat slab. Before that, let us discuss about the design methods of flat slab. Flat slabs are designed by two main methods, either by Approximate Method, which consists of the column strips and middle strips, or the second one, which is more accurate, that is a finite element based method. In the Approximate Method there are two types. One is the direct design method, which has the advantage of being the most simplest, most highly used, easy hand calculated type of method. However, the disadvantage of using direct design method is A, it is approximate, B, it requires 3 minimum spans in each direction. So when it comes to an irregular flat slab having staggered orientation of columns, it is absolutely inappropriate to use this particular design method. Then in case of exterior panel design, the results are not accurate. When it comes to equivalent frame method, to overcome some disadvantages from direct design method and provide better results, then however, the disadvantage of the equivalent frame method again is it requires minimum 2 spans in each direction. then it's not accurate. So let's talk about the finite element based method that will overcome all the disadvantages of the approximate method. Advantages would be it is appropriate for any type of flat slab, rectangular or irregular, no problem. No restriction on orientation of the columns or any loading pattern. It can perform linear as well as non-linear analysis. And you can, in that case, perform the serviceability deflection check very accurately. The only disadvantage with finite element based method would be the mesh size control, which we recommend as L by 5 to L by 15. So in MIDAS Gen, we have provided the most accurate method, that is finite element based method, and along with that we are going to be performing the flexural design. So once we have extracted the results from the analysis, that is the MXX, MYY and the MXY results, flexural and torsional results, these results are in the local plate element axis, right? So now we need to find out the moments as per the orientation of the reinforcements that is required by the user. So under the subdomains, we provide the reinforcement direction with respect to the global axis. Now, so the next part comes about the reinforcement direction 1 and 2 with respect to the local axis. So the software will take into consideration the alpha and phi values for the direction 1 and 2 reinforcements, convert the MXX and MYY and MXY values, which are in the XY coordinate system, to MA, MB and MAB moments in the AB coordinate system. And after these moments are transformed, they are going to be used for calculating the wood armor moments. The wood armor moments in the direction 1 and direction 2 for the bottom and top are calculated by using these formulae. So these are the bottom rebar wood armor moment calculations, and similarly we have the top rebar moment calculations. These moments are going to be used further for performing the flexural design as per the American standard. So let us see that in MIDAS Gen software. Firstly, we'll select the design code. So that is ACI318-14, and we'll click on OK. Further, we'll go to the mesh design, and then we can check with the slab load combinations for flexural design. So we'll see under the strength. So all these three load combinations, with their description is right over here, are going to be used for performing the design. So we'll click on OK. Then we'll go to the design criteria for rebars. If you want the software to entirely perform the design entirely, then you can uncheck this. So using these rebars, the software will provide the reinforcements, and this is the spacing that you can restrict it to use. And further, there's effective cover which you can provide, or the software can calculate by itself. Okay, so I'll click on OK. Providing the rebar information to the software, I can go ahead and perform the slab flexural design. The slab flexural design, I want it to be performed as per the average nodal values. I want to see the top in the direction 1, the reinforcements that the software is providing. It can provide me with the rebars, the required steel, the ratio of required steel, and the resistance ratio, and also the wood armor moment. So I'll click on apply. And the software has provided the information, rebar information. So maximum rebar at the supports is 12 at 100. and further it is providing 10 at 400, which is the least area of reinforcement. Similarly, I can get for the bottom direction. Okay, so maximum I would require 12 at 300 and minimum 10 at 400. Okay, so this is the reinforcement provided by the software. We can see how the design has been performed by checking the design result. Okay, so as you can see, a summary has been provided with the bottom and top reinforcement information. Then further, as you can see, the reinforcements and the AST required, AST used, and the and the formula for calculating the moment of resistance and the ultimate moment is checked and it's okay. So in this way your flexural design is taken place, and the detailed report is generated for each and every element that you select by the code. You can save this file, copy paste it into your Word file or Excel sheets anyhow. Also, I can see the design forces for which the software has performed the design. So these are the the wood armor moments in the direction 1, the top direction 1, bottom direction 2, top direction 2. Similarly for bottom direction 1 and bottom direction 2 for each and every element. Further, I can use these reinforcements to perform my cracked section analysis. So for that I can simply click on update rebar and close this. So after I click on update rebar, over here all the reinforcements are randomly assigned to the elements. However, when it comes to practice, we are supposed to provide the reinforcements to uniform reinforcements. So for that reason, what we're going to be doing is we'll be assigning the reinforcements onto the slabs by using the subdomains that we have generated. So these are many subdomains that we have. So instead of having all these subdomains, individual subdomains, what we can do is create only 2 subdomains. I'll delete this. One will be for the support and one will be for the middle strips. So for assigning the subdomains to the elements, all I have to do is just simply firstly select all and drag and drop the first subdomain, and then I'll go to the top view. I'll display by double clicking on these elements, or I can just double click on these dummy elements and I can see the divisions. So I can simply select all these slab elements, plate elements, and then I'll drag and drop the second subdomain. Okay, so now for easy selection, I've got over here these 2 subdomains. So firstly, let me assign at the support the reinforcements. So I'll assign the maximum top reinforcements at the support. So that will be P12 at 100. I'll drag and drop that. Okay, then for the center, here I'll provide the reinforcement 10 at 300. Then I can provide the bottom direction 1. So this is P10 at 400 and 10 at 300. So instead of that, I can simply select the entire slab and assign 1 reinforcement, that is 10 at 300 at the bottom. Okay, the rest which are blue are not going to be considered. You can keep them or delete them. Okay, and then we'll have top direction 2. So for the supports, the maximum reinforcement 12 at 100. I'll simply select all of these and drag and drop this 300 over here. So I've got P12 at 100 and 10 at 300, top direction 2. And further I will provide the bottom direction 2 simply 10 at 300 for all the elements. So I'll select these as well as these and drag and drop 10 at 300. Okay, so all the rebars in black have been assigned. I can delete the rest. No use. Okay. So in this way I have assigned the rebars to my entire flat slab. Okay, so after the rebars have been assigned, I can go ahead and perform check. So that is the slab flexural checking. So now it will check with the rebars that has been provided by the user. So I'll click on apply. Okay, so this was the bottom direction, which was only 1, so I'll just keep it both. Okay, so this is the top direction, 12 at 100 and 10 at 300 had been provided. We can see now the resistance ratio for checking. So it is failing for some locations. It is 1.77, most probably at the locations where the supports, negative supports are there. Negative moments are there at the supports, so we can ignore that part because it comes under the rigid zone. We can as well see the design result just like we had seen for the flexural design. So this was about the slab flexural checking. Now let us go back to the presentation and discuss about the slab shear checking that is available in MIDAS Gen. Shear checking of slab as per the American standards is available in MIDAS Gen. Shear checking is one way as well as two way. Two way is the punching shear check. So this punching shear check are the results at the supports of the slab elements or at the concentrated loads. And we have one-way shear check result that is going to be along the user-defined shear check lines. Now the punching shear check can be performed in two ways. One is by code and other is by finite element method, that is the stress method. By code, the program takes the actual force of the column supporting the slab, that will be the VU, and the maximum shear force will be summed up with the unbalanced moment, that is gamma VMU, as per the clause 13.5.3 of the ACI standard. After we have the shear force, the shear resistance of the slab is calculated using these three formulae. These are the equations taken 1131 to 1133 from the ACI standard. Then it will check with the resistance and with the force and the resistance and see if it is safe. If it is not safe, then the software will provide the shear reinforcement. However, for providing the shear reinforcement, it is mandatory that the slab thickness is greater than 200 mm, which is approximately 16 times the shear rebar diameter. And the reinforcement is calculated using this formula. The other method of finding performing the punching shear check is by the finite element method. In the finite element method, we know the shear forces at every node of the finite element. So these forces are then interpolated, and then at the critical section the force is taken and it is divided by the effective depth of the slab, and the shear stress is then calculated. The advantage is that there is no need to calculate any beta to consider the moment transfer to the columns in this method. So this shear stress that is supposed to be taken into consideration for performing the punching shear check also has two methods in MIDAS Gen. You can do it by average by elements, or we have average by size. So we can see all this in MIDAS software solution. This is the punching shear check by the code as well as by FEM. So this is average by segment and average by side method. Then in the code, in this session we'll be performing the punching shear check by code. So we'll check on the code over here and then we'll click on apply, as well as we'll see the values. So here it provides us with the ratio, demand capacity ratio, and all have passed. So like I mentioned earlier, we can check the critical section that the software has taken into consideration. So for that I'll just check on the hidden. So this is our column, and the critical section is around the column at a distance d by 2 from the face of the column. We can as well perform the one-way shear check along the cutting line that we have defined. So I'll define a cutting line along this particular line. Click on add and then click on apply. So what the software does is it performs the one-way shear check and provides the result right over here with the ratio as well as the demand capacity ratio as well as the required thickness. So we have provided thickness as 180, which is much more than the required thickness. This punching shear check report is also created by the software. So for that we'll click on design result. So as you can see, the shear stress capacity of concrete information is there, and the forces and results. So the ratio is further checked, and the requirement of reinforcement is recommended by the software, if it's required or not required depending on the demand capacity ratio. Similarly, we can see the one-way shear check that has been performed. This software is not a black box. All the formulae are right over here, and according to these formulae, the software calculates the values and produces in front of you. We are good to go ahead now and perform the serviceability check. So before that, let us see how the software performs the serviceability check as per American standard. So here we can perform the serviceability check by firstly providing the parameters, and the software can perform the serviceability check for the uncracked section property as well as for the cracked section property. So this is how the stresses are calculated for the uncracked section, and the verification is performed. Then further, in case cracked section analysis is required, then we have to provide the rebars to the software. We have to assign the rebars to the slabs and then perform the cracked section analysis. The software calculates the cracked moment of inertia by using this formula from the American standard, and these are the parameters that the software will automatically calculate internally. Now when it comes to cracked section analysis, the effective moment of inertia is supposed to be calculated. So this is as per the Branson's model. So this is the average value for the moment of inertia along the length of the member, and it is along the length of the member. The cracked moment is calculated using this formula as per the American standard internally by the software. And also the modulus of rupture of concrete is not required to be provided by the user. You can this is taken care by the software itself. In order to perform the cracked serviceability check, we have to go through the following steps. Firstly, we define a subdomain and input the rebar information. Then we check the slab rebars that we have provided under the subdomain by performing the check if any additional bars are required or not. After the rebars have been assigned to the slab, we can go ahead and perform the cracked section analysis. So before that we have got the analysis control as well, in which number of iterations and conversion tolerances can be controlled by the user. After we perform the cracked section analysis, we can go ahead and check the results. So this is what we're going to be doing right now. We will go step by step. Firstly, we'll check with the load combination. For serviceability check, we have got dead load and dead load plus live load combination, and we are also using the same for performing the cracked section analysis for deflection check. Further, let us provide the serviceability parameters. So deflection control can be deflection control limits can be provided from here. This is as per the code. Default values are provided, you can just check them on, or you can have user defined limit. So I'll be using the default limit, and you have to select all the elements and then click on apply. Then further we'll go ahead to the cracked section analysis control. Here the number of iterations per load case and the convergence tolerance will be controlled by the user. So I'll click on OK here, and then go ahead and perform the cracked section analysis. As we know that we have already updated the rebars, and then we have done slab flexural check as well by assigning the rebars to our subdomains. So it's now okay to perform the cracked section analysis. So cracked section analysis has been performed. We can go ahead to the slab serviceability checking. Here I can select any load combinations, and all load combinations mean the critical value will be used for performing the serviceability check. So I can have the deflection check for uncracked section as well as cracked section. That too, I can have it immediate, or I can have long-term cracked deflection. This will include the creep and shrinkage, and this will include only the creep. So I'll include the long-term deflection as per the creep and shrinkage both. I'm keeping it 5 years or more, and then I can click on apply. So the software has performed the cracked section analysis and also has provided the deflection for the long-term cracked deflection. I can as well check the design result. So out of all the elements, particular elements for the top and bottom are going to be shown. So element number 1030 is the critical element where the maximum deflection is taking place. So it has provided the immediate crack deflection as well as the long-term crack deflection, and it has checked with the deflection limit that we had provided, and OK or not good would be displayed. We can as well see the crack points wherever the cracking has begun on our slab. So click on apply. So I would like to conclude that we have performed flat slab analysis, checked the analysis results, performed the flexural design where the software has provided reinforcements. We can provide our own reinforcements and have the software check them and provide us the report. Then we have performed the slab punching shear check. There are various methods that were discussed available in MIDAS Gen for performing punching shear check. And finally, we performed the cracked section analysis for serviceability check, wherein we got immediate and long-term deflections for uncracked as well as cracked section property. So as you can see over here, we have also got the output in the form of a report, and also we can check the location of the crack points. Okay, if you have any questions, you can write to us at techsupport@midasit.com. Thank you very much for attending this session. We hope to see you again for the next session, which is going to be held on 18th on column shortening analysis. If you're interested, please register.